these value we have completed in the last class. Yes, Aram, how was your exam? Aram, I think your exams were going on, no? How was there?
It was a little tough, but I managed to do.
Okay, so when the results will be displayed?
I think within a week.
Okay, okay. Do send me your question paper once on WhatsApp, Aram. All right.
Yeah.
Okay, class. So yes, this question was left. Just try to do it. I'll discuss it with you. First, try to attempt it. Critical velocities formula we did, turbulence and liquid flow we did it. Fine. This was one question was left. We'll do this. First, note it down. Try it yourself. Send me the solutions and I'll discuss it. See the solution for this. It says that the flow rate of water from a tap of diameter 1.25 centimeter is 0.48 liters per minute. Coefficient of viscosity is given. Coefficient of viscosity eta. Eta is given as 10 to the power minus 3 Pascal seconds. Now, after some time, flow rate increases to 3 liter per minute. Fine, you have to characterize the flow. Characterize the flow means whether you have to state whether it's turbulent, whether it's streamline, what is it? That is what is meant by characterize it. Now see, Q1 is given as, that is fluid flow is given as 0.48 Liter per minute, it means it is by 1 minute. So we have to convert it in seconds. So this will become 0.48 into 10 to the power minus 3. I have converted this into meter cube and this will be by 60 seconds. Now this is in SI unit. So this will become 0.08 into 10 to the power minus 4 meter cube per second. Eta is given as 10 to the power minus 3 Pascal seconds. We'll be having value of Q2 as well, same way, 3 liter per minute. This also we'll convert. So Q2 will become 3 liter by 1 minute. So it will also, this will also become 3 into 10 to the power minus 3 divided by 60 seconds. So this will become 0.5 into 10 to the power minus 4 meter cube per second. So this is Q1, this is Q2. Now when you have to find out the rate of flow, see, rate of flow will become volume by time, right? So volume is area into length and time is T. Now see class, area into length, this is volume by time. Length by time is velocity. So this becomes A into V. This relation we are going to do also. Q is equal to AV. This is constant. This is one equation we use. AV is constant. So here also directly not writing, I'm getting this value. Now see, fluid flow. This will actually be area is pi r square. Velocity is V. Or write it in terms of diameter since diameter is given. So pi d by 4 whole square into velocity. I've just kept the value of Q here. Now see, once I have the value of Q, now I'll be putting Reynolds number. So once you put in Reynolds number, Q value you have, see NR. NR1 will become, see, Reynolds number is basically rho VD by eta. Rho VD by eta. Or you can do one thing, you can put the value of V as pi d square by 4 as well. Same way you can put it. So here what you could do, you get this as 4 into 1000. Why 4? C class. What you can do is you can write this as rho. Fine. Here you have pi d by 4 whole square. So put it that way only. So that 4 will come up. 4 by pi d square. Here 1d you have q by eta from the previous formula. dd will get cancelled from here. So that becomes 4 into 1000 into 0.08 into 10 to the power minus 4 divided by 10 to the power minus 3 into 3.14 into 1.25 into 10 to the power minus 2. This is NR1. So I think when you solve this, you will get this as 815. Same way calculated for NR2. That you will get as NR2 will become 5096. Now see, this is lesser than 1000. Lesser than 1000. So this flow becomes streamline. This flow becomes streamline. And this is more than 2000. This flow becomes turbulent. So this way you calculate Reynolds number and use the value of fluid flow that is given. Note down the solutions. Wherever doubts you are having, ask me. Anyone wants to see the question, just text me. I'll show up the question. How much it came? 815.28. Okay, so exact is 815.28. Yes, so that's why it becomes streamline. Next, we have equation of continuity. Now, equation of continuity is the same equation. This equation only, no? A1 V1 is equal to A2 V2. It means, this basically means that area and velocity both are inversely proportional. So wherever there will be lesser area, more velocity will be there. A narrower end of a tube will lead to greater velocity of particles. Whether it is fluid flowing, particles are moving. If area is less, velocity will be more. If area is more, velocity will be less. So this equation is known as equation of continuity. You can keep on adding A1, A V1 is equal to A2, V2 is equal to A3, V3 is equal to A4, V4, and so on. So for streamlined flow of an ideal fluid, the rate of fluid flow is constant. This is it. So you have the applications of this mainly in Bernoulli's theorem. Mainly you have this in Bernoulli's theorem. So this is the equation of continuity. Equation of continuity states that the mass of a liquid flowing through a pipe of varying cross section is constant when the density of the liquid does not change. Therefore, equation of continuity is a statement of conservation of mass. Mass is only getting conserved, no, because mass is getting conserved, then only we are having these values. So A1 V1 is equal to A2 V2 will be used. This equation, continuity equation, this will be used, especially in Bernoulli. So note it down first. See, here in Bernoulli's theorem, we basically have conservation of certain energies. So before we exactly start with Bernoulli's, I'll discuss some of the energies. Like we have potential energy. So all of you know potential energy is mgh. Now potential energy per unit mass. Potential energy per unit mass divided by m. So this becomes mgh divided by m. This becomes only gh. Now write potential energy per unit volume. Potential energy per unit volume. So that becomes mgh divided by V. Now mgh divided by V, so that becomes, see from here mass by volume is density. So this is only rho gh. So you have gh from potential energy per unit mass, and you have potential energy per unit volume as rho gh. Next, you have kinetic energy. Now, basic formula of kinetic energy is known to you. That is half mv square. See, this is half mv square. Now, kinetic energy per unit mass. So, divided by mass, half mv square divided by mass. What is left? V square by 2. Kinetic energy per unit volume, half mv square. See, mass by volume is giving you density. So, half rho v square. Then you have pressure energy, the third type of energy. Now, why are we having pressure energy? This is because fluids, we have seen pressure exerted by liquid column, pressure exerted by solid sphere, and all these different cases we had also seen. So pressure energy is basically whatever energy is pressure that is exerted by the liquid. Whatever fluid the container contains, the pressure exerted by that liquid, that is known as pressure energy. So it's in totality, you can refer to it as the energy that is your work done, mainly conversion of work done. Now see, work done here, pressure energy, since this is work done. So your pressure energy, this is actually P delta V. This is P delta V. Delta V is change in potential. Sorry, change in volume. And P is the pressure exerted by liquid column. This is pressure exerted by liquid column, you can say, or directly liquid also. One more thing, class, see, if you divide pressure energy by volume, you will get P delta V by delta V. That is pressure energy per unit volume is pressure energy only. Remember, this is not potential energy. This is pressure energy. You can put R also here to differentiate. So these are the three types of energy that we relate with Bernoulli's theorem. First, note down all of these. Then we are going to conserve all of these energies in Bernoulli's theorem. Now see, coming to the main statement of Bernoulli's theorem. So three energies we discussed. One was kinetic energy, one was potential energy, second was pressure energy. Now Bernoulli's theorem, it states that for steady flow of ideal fluid, total energy, not in total energy, you'll have all the three energies. Which three? Pressure, potential, and kinetic. So pressure, what we'll do, we'll represent pressure energy by PE and instead represent potential energy by U. That would be better because symbols will become very confusing then. Now see, for this we have to plot a derivation. There's a derivation for this that can be asked and is usually asked in long answer questions. So see what I'll do. I'll take a random pipe. But before that, let me write down all the three. Let's say this is pressure energy. Let's say this is half rho V square kinetic energy plus rho GH potential energy. This is constant. This is what your energy is. Now coming to the derivation part. See, in the derivation of this, I am taking a random shaped pipe. This is one end of it and extended to some random height also. Like this I have taken it. Fine. Like this I have taken it. Now from, if let's say this is the ground level, this is H1 height. And from there, this is H2 height. Right, this is H1, this is H2 height. Fine. So some things let us take like this height distance we have taken. Let's take the diameters. D1, area is A1, velocity is V1. Let us assume this. Same way here also, A2 here, V2 here. And this is D2 here. Now see, here what will happen? When the fluid will flow inside. So P1 will be the pressure. And from here, when it will be moving outside, this will be P2. Fine. Now see here, if you look at the N1, I'm referring this as N1 and this as N2. If you look at the force at N1, we know the pressure is P1, we know the area is A1. So force will become pressure into area. Pressure is force upon area. So force will become pressure into area. So F1 will be P1 into A1. Fine, P1 into A1. Then you have, if you find out the work done here at this edge, work done. So what will happen if you find out the work done? That will become force into displacement. And now force's value is P1A1. So put it here. The value of force I am keeping here. So that will become P1A1. So if you put it P1A1 into D1. Now, what we'll do, distance also we are writing this diameter as V1 into T, speed into time. We are writing that also as speed into time, right? So complete work done. Value of complete work done, just a second. So value of complete work done, it will become P1 A1 V1 into T. Now same way if you want to find out the work done at the second end, that will become P2 A2 V2 by T2. But just a difference, there will be a negative sign. Why negative sign? Because here it is decreasing, it is going out. That is how you have to remember for your exam as well. Here fluid is coming out. Like if you see from here, fluid was moving. It is exiting this path exactly. Random motion of fluid. Do not draw a straight horizontal pipe because that will become a special case. We'll do that, don't worry. Yes, we will do that. We are going to do. Now see, so net work done will be what? This is work done 1, work done 2 is there. So net work done will become P1 A1 V1 T minus P2 A2 V2 T2. Now volume of fluid that is entering the first edge, it will be exactly equal to volume exiting the first edge, right? Volume of fluid that is entering end 1, it is exactly equal to volume leaving edge 1, leaving edge 2. Fine. So here it will become, apply continuity equation, volume becomes A1 into V1 into T is equal to A2 V2 into T2. Why? Because delta V is volume of fluid flowing in same time T. Now C class, work done. Work done will become P1 delta V minus P2 delta V. That was the change in the work done. So if you take delta V common, you get P1 minus P2 into delta V. That is the total energy, pressure energy. You have kinetic energy as half mv2 square minus half mv1 square. You have potential energy as mgh2 minus mgh1. If you take the net difference of all the energies that are present, right? Now see, completely, if you write this, work done will become P1 minus P2 delta V. This is equal to kinetic energy is half mv2 square minus half mv1 square plus mgh2 minus mgh1. Even if you multiply this, you're asking for multiplication. See, even if you multiply this separately, P2 delta V like this, same thing, no difference. This will be exactly the same. Understood? Now see, what are all these terms? See, P1 delta V plus half mv1 square. This is initial pressure energy. This is initial kinetic energy plus mgh1. This is initial potential energy. Then P2 delta V. This is final pressure energy plus half mv2 square. This is final kinetic energy plus mgh2. This is second potential energy. This is second potential energy. Now, had there been a third, you would have added that also. Had there been a third type of energy, let's say 3 energies you are getting. So is equal to P3 delta V3 plus half MV3. Then for fourth one, it will keep on getting added. Why? Because this sum will remain constant. This is exactly what is your Bernoulli's theorem. Fine. So this is derivation. Is there a slight long derivation? Note down all these points. Wherever derivation part you're not able to understand, let me know. This question comes in your exam. Bernoulli's theorem is important. See, if the pipe is horizontal, horizontal means both the heights are same. At edge 1 also and at edge 2 also. We had taken a random pipe where height 2 was greater than h1. If both the heights are equal, then see, directly pressure is inversely proportional to velocity. That is clear. So you will not use mgh component. You will just use P1 plus half rho V1 square is constant. That's it. Not mgh component if the pipe is horizontal. Note it down. That now try this question by yourself. Then I'll discuss it with you. First, note this down, pipe part, then start with the question. And those who will get the answers, share it in the chat column. Yes, you will use A1, V1 is equal to A2, V2. Then only this question will be solved. Yes, 1 meter per second. Good. So if you have calculated this, can you calculate P2? Last 1 minute and I'll discuss it. Okay, so I think only Tarif has tried it. No, I think slight error. How much? 2.75. Yes, correct. Good. So, entire question you have solved it correctly, Tari. Good. So only you have done it. Now, see, question says that water is flowing through two horizontal pipes of different diameters, which are connected together. Now, in the first pipe, the speed of the water is 4 meter per second. Pressure is given as 2 into 10 to the power 4. So apply P1 plus half rho V1 square is equal to P2 plus half rho V2 square. See, P1 is given as 2 into 10 to the power 4. Density is 1000. V1 is 4 meter per second. But main problem is that for calculation of P2, we need V2 as well. Otherwise, how you'll solve the equation? See, if I put all the values, 2 into 10 to the power 4 plus half into 1000 into 4 square is equal to P2, which is unknown, plus half again 1000 into V2 square. This is also missing, no? So for that, we'll use A1 V1 is equal to A2 V2. Area is pi d1 by 2 whole square. V1 is pi d2 by 2 whole square V2. D1 square V1 by D2 square is equal to V2. So V2 will become 9 into how much? 9 by 9 into 4 by 36, right? So that will be again 1 meter per second. So your answer, see, this becomes 20,000 into 500 plus 3. So 28,2800. This is equal to P2 plus half into 1000 into 1 square. That is 500. So P2 will become 27500 pascals. This is the answer. Note down the solution. Whichever step you're not able to understand, please get it clarified, class. Write it from here. All right. Okay, class, you can leave now. Now we'll continue this on Wednesday. Applications is left and Torsily's theorem. So most probably we'll complete with the lesson on Wednesday. Okay, thank you so much, class.
Thank you, Miss.